Hello, my name is Jaime Garcia Jr., and this is my final OREU update. I am a junior at UTRGV, majoring in mechanical engineering with the hopes to focus in material science. My mentors are Dr. Brady Butler, Nicole Persons, and Daniel Lewis, and this work was supported by Los Alamos National Laboratory. Hypersonic aircrafts allow us to reach speeds never thought possible. We can travel greater distances and at a speed of 5 times the speed of sound, which is approximately 1,715 meters per second. However, the extent of our progress is limited by the materials that we use, as their properties will dictate what they can endure and for how long. The Concorde, for example, is traveling at Mach 2, twice the speed of sound, and already reaches temperatures of 127 degrees Celsius at the nose tip. These temperatures easily get hotter than 1500 degrees Celsius as the altitude decreases and as we reach higher speeds, such as Mach 5, which is hypersonic. The material property of our aircraft will be very important in determining the safety at such speeds. To better understand the mechanical properties of these materials, we will be using a mini tensile tester to accurately understand the material's mechanical behavior. We like the facilities capable of performing tensile tests in such extreme environments, but due to the small form factor, we will be able to perform numerous tensile tests in a rapid manner. However, the materials to make this tensile tester are expensive, so we will be utilizing 3D modeling and simulation to see if our designs will survive simulated thermal and stress tests to ensure we do not break any components. I have been tasked with recording the behavior our grips will undergo and how the heat is dispersed throughout the parts, more specifically the grips. To model our grips, I will be using Autodesk Fusion 360, as it is great at displaying von Mises stresses. The von Mises stress shows a complex stress state at a point and helps us know if yielding will occur. Fusion 360 allows us to see the von Mises stress throughout the entire model, and this allows us to see where we need to redesign if possible. The grips here have the highest von Mises stress towards the sharp corners, so maybe we can do more research into changing the geometry there. As we can see here, they are yellow, and getting closer to red, which is on the higher end of this von Mises stress, which is in megapascals. The grips will experience a 1 kilonewton force spread throughout the two interfaces of the grips to simulate a tensile test. A triangulated mesh covers our 3D modeled samples, and the accuracy of these simulations increase as we make our mesh finer and finer so that it accounts for a truer shape. Since there is a high von Mises stress near the sharp corners of the grips, we can apply a fillet to smooth out the inner extrusion and see how this affects our von Mises stress. This is a maximum deformation of the grips at 5% of the model size. As we can see, it stretches outwards, which is not good. Manufacturing restrictions prevent us from making a single grip, so we will have to bond two pieces together. Since we are using a two-piece grip, we want to see if a fillet on the grips has any effect on lowering the max von Mises stresses. We intend to reach 900 degrees Celsius and work our way up to 1200 degrees Celsius. So we will use Hastelloy X for the grips due to its high temperature strength and oxidation resistance at high temperatures, such as 900 degrees Celsius. Regardless of the fillet type that we tested, two-piece grips had lower von Mises stresses than the single-piece grips. And regardless of the width of the sample, the base fillet consistently had a lower max von Mises stress compared to the largest fillet samples for our two-piece grips. So we will be using a two-piece grips with the base fillet to minimize our max von Mises stress. The safety factor of the grips were the highest with the two-piece grips, and the base fillet had the highest safety regardless of mesh size. So that's also a plus. Since we will be using the two-piece base fillet, we will use thermal simulations to ensure that the heat is dispersed such that our load cell is not damaged. The load cell is delicate and will break if it approaches 100 degrees Celsius. We would like to simulate thermal dispersion in open air for 900 degrees Celsius and in a vacuum-like condition as we reach temperatures closer to 1200 degrees Celsius. This was my first time really using any sort of thermal simulation, so I followed the thermal radiator problem that Fusion 360 provides for free to better understand setting up a thermal simulation. And so basically what we have to do was we needed to set our boundary conditions, which we used to simplify our problem. For the radiator example, we removed the bolts located towards the end of the pipes and focused on the water inside the pipes, and the heat transfer to the fins. We then set the water to 75 degrees Celsius and apply a radiation load on the contacts between the radiator fins and the pipes, with an ambient temperature of 20 degrees Celsius to simulate room temperature. We then apply a convection load of 5 watts per millimeter squared Kelvin between the fins and the pipes to simulate thermal conductivity. We will keep the mesh at coarse to shorten our processing time, and we can see that the pipes here is where the hottest parts occur, and the fins cool to around 65 degrees Celsius. We use our understanding of thermal simulations to set up the problem for our load cell. We apply a thermal load of 900 degrees Celsius at the face of the grips and a convective load of 20 watts per millimeter squared Kelvin on the face of each part to simulate open air. And after running the simulation, we see that the load cell stays cool at around 27 degrees Celsius, so it is safe. Thermal simulations are not without flaw, however, as there were issues with the mesh of the simulated air and the insulation of the models. I believe this is due to the usage of boundary fill, which essentially allows us to select numerous objects and subtract the pieces of that model to create a new component with the leftover volume. But this could also be due to the insulation having a simple geometry as opposed to a fluffy consistency like the real thing, such as cotton. I was also not sure if it was possible to simulate low pressure conditions in Fusion 360, so I was unable to successfully simulate the samples in a vacuum. However, future work can be done to progress the thermal simulations. ANSYS in particular has a complex finite element analysis that can better simulate the thermal properties of the grips at 1200 degrees Celsius. As you can see here, it shows the flow of heat, which I have yet to see in any Fusion 360 thermal simulation. More research can also be done into materials such as carbon-carbon composites, tungsten rhenium, and cermets. Could be looked into for the higher end temperature tests. And if the heat is an issue for the load cell, as we get closer to 1200 degrees Celsius, we can incorporate a water cooler to keep the grips cool and prevent the load cell from frying. This work was supported by Los Alamos National Laboratory. I would like to thank Los Alamos National Laboratory for the funding and the ARL team for their feedback and guidance throughout this entire internship. These are my sources cited, and thank you for your time and listening. I hope you guys have a great day.